Hello friends, today we are going to see a session from Group Theory 2, Group Action on a Set. A group action is where a group of symmetries act on a set, usually a set of vertices, edges or faces to give the same set, and we use the example of a particular rotation of a symmetry of a regular tetrahedron to explain the concept. So, to explain it more, let me consider another example, that is the regular octagon acting on the set of vertices. If we denote R as the anticlockwise rotation of 45 degrees, then R acting on the vertex 1 will give 2, R acting on 2 will give 3, etc. On 8 will give 1. And note that the output which is given on the right hand side column is just a rearrangement of the input given on the left hand side. So this is not just a coincidence. This comes from the definition of symmetries, because in this case the symmetry preserves the octagon and its 8 vertices as well. So the action of any symmetry on the vertices would rearrange them. Not every rearrangement is a symmetry. For example, let us consider just swapping the 2 vertices in the octagon. We can clearly understand that we use here, whatever we do here is not a symmetry. So it is more convenient to consider all these symmetries, not just some of them. And this is more officially defined as permutation. We can establish that all symmetries is a permutation of one of the vertices, but not the other way. The reason why we discuss permutation is that in a sense it represents symmetry. After all, if we discard the notion of distances, then the permutation like this will represent a symmetry. Not that the subject under consideration are the 8 vertices and all the 4 properties of symmetry will hold for permutations as well. Hence, the permutation would form a group. For some reason, it is named as a symmetric group, even though it is not about symmetries. Just to summarize what we have done, we have a group of symmetries of an octagon acting on the set of vertices. For every symmetry, say the horizontal reflection, we can always discard the figure and just look at how the symmetries act on the vertices, which means all symmetries correspond to a permutation. The correspondence is formally constructed as a function, say phi. This function sends an element from the group of vertices, and it's not complicated. Just understand that it sends each symmetry, say for example the horizontal reflection illustrated in the previous example, to the corresponding permutation, which we abbreviate as G star. So this function is not a normal function, it is a homomorphism. Why? Consider phi of h into phi of g. That is, we are doing the permutation corresponding to G first and then followed by the permutation corresponding to H. This is a permutation corresponding to the symmetry H into G or HG. So that this is simply phi of HG. So this satisfies the definition of a homomorphism. In short, whenever you have an action of symmetry G on a set X, you will have a homomorphism from G to the collection of permutations of the set X. Here we just use the example of symmetries of the octagon, and the correspondence of the action is very useful. The very clear application of this is in the proof of Cayley's theorem. Everything that we will discuss now will be more abstract than the set of vertices that we have discussed. This change in perspective is the proof of the theorem. But it will be very useful to have this mental picture that the elements in the abstract set X are just the little dots, and the group action just somehow rearranges these dots. With that all said, let us see the proof of Cayley's theorem. Cayley's theorem states that every group G is isomorphic to a subgroup of symmetric group of G. So what does Cayley's theorem say? Cayley's theorem states that every group G is isomorphic to a subgroup which is a symmetric group of G. So looking at the correspondence once again, it looks like the set X is the group G itself. It is quite different from what we did, but the action we will be considering will be very simple. So if we act the symmetry G1 on symmetry G2, then we must just get a symmetry corresponding to doing G2 first and then G1. So going back to the visualization of the group action using these the dots that we have, or else the vertices that we had of the octagon. So each of this now will be just a symmetry. So one dot may represent the identity, the other one would represent the symmetry G, and another one would be H, etc. Another one can be its inverse somewhere in the 8 dots. So we may have another symmetry H and also another one which is GH, and so on. Okay, because of the action we defined have this form G1 star G2 is equal to G1 G2. When we consider the action of this G on the symmetries, the identity would become G itself. Because doing an identity symmetry first and then G is same as G altogether. Then G inverse would be sent to the identity, because undoing G and then doing G is same as doing nothing, and that is the identity. Then the action of G on other symmetries would look something like this, where every single symmetry H corresponds to the permutation of the dots which are symmetries themselves. And this seems like we have a ready proof for Cayley's theorem, because we showed that every symmetry will correspond to the permutation of these symmetries.